How do we do genetics, even though we can't arrange the matings the way we'd like to? Sorry? Well, family trees. We have to take the matings as we find them in the human population. You can talk to somebody who might have an interesting phenotype. I don't know, attached earlobes or very early heart disease or, some unusual color of eyes, and begin to collect a family history on that person. It's a little bit of a dodgy thing because you might be just relying on the person's recollection. So if you were really industrious about this, you'd go check out each of their family members and test for yourself whether they have the phenotype. People who do serious human genetic studies often go and do that. They have to go confirm either by getting hospital records or interviewing the other members of the family, et cetera. So this is not as easy as plating out lots of yeasts on a Petri plate. And then you get pedigrees. And the pedigrees look like this. Here's a pedigree. Tell me what you make of it. Now, symbols. Squares are males. Circles are females by convention. A colored-in symbol means the phenotype that we're interested in studying at the moment. So in any given problem, somebody will tell you, well, we're studying some interesting phenotype. You often have an index case or a proband, meaning the person who comes to clinical attention, and then you chase back in the pedigree and try to reconstruct. So suppose I saw a pedigree like this. What conclusions could I draw? Sorry? Recessive. Sex-linked trait. Why sex-linked trait?
Because it's the male who has it there, and then it could be passed on to the X chromosome to the female, and then it's because the Y chromosome is dominant over the X chromosome.
So let's see if we can get your model up here. You think that this represents sex-linked inheritance. So what would the genotype be of this male here? Mutant, I'll use M to denote a mutant carried on the X chromosome, and a Y on the opposite chromosome. What's the genotype of the female here? So it's plus over plus, where I'll use plus to denote a normal X chromosome, the gene carried on the normal X chromosome. Okay, and then what do you think happened over here? So mutant over plus, you mate to this male who is plus over plus. Why is that male plus over plus? Oh, right, good point. It's not plus over plus, it's plus over Y. Why is that male plus over Y as opposed to mutant over Y? He'd have the mutant phenotype, so he doesn't have the mutant phenotype, so we can infer he's plus over Y. Okay, and then what happens here? Mutant over Y. This is plus over Y. How did this person get plus over Y? They just got the plus from mom. And the daughters? Y from dad. And a plus from mom. No, that's cool. Now, what about the daughters here? They're a plus over plus? Or M over plus is 1, 1, and 1 the other? Well, in textbooks, it's always plus over plus and M over plus. But in real life, we don't know, right? So this could be plus over plus or M over plus. We don't know. Okay? Now what about on this side of the pedigree here? What's the genotype here? Plus over Y. Okay. Why not mutant over Y? Because if we got the mutant, it would have to come from the... Okay, so here plus over plus, and then here everybody is normal because there's no mutant allele segregating. Yes? Yeah, couldn't this just be recessive? I mean, it's a nice story about the sex link, but couldn't it be recessive? So walk me through it being recessive. M over plus, plus over plus. Oh, so wait, hang on. Could this be M over plus and that person be affected? It's got to be M over M, right? So mutant over mutant. But that's possible. Yeah, okay. So what would this person be? Plus over plus, let's say. Come over here. And now let this person be. M plus has to be M plus because, okay. And what about this person here? M plus. Now what about the offspring? So one of them is M over M, plus over plus, and two M pluses. Does it always work out like that? No, it doesn't always work out like that at all. So I'm just going to write plus over plus here, just to say tough, right? In real life, it doesn't always come out like that. What about over here? It would have to be plus over plus. Why not? It doesn't, because it could be M over plus and have no affected offspring by chance, right? But you're going to say it's plus over plus because in the textbooks it's always plus over plus in pictures like this, right? And then it all turns out to be pluses and mutants and pluses and mutants and all that, right? Well, which picture's right? Sorry? You don't know. So that's not good. There's supposed to be answers to these things. Could either be true? Which is more likely? The one on the left, why?
It's more statistically probable.
More statistically probable. How come? Because it is. It may not quite suffice as a fully complete scientific answer, though. Yes?
Because if you had the carrier trait
Yep.
as an X, there's only going to be, you only need it two, okay, there you would need two M's for a mutant.
Well, but I have somebody who is affected here. So given that I've got an affected person in the family,
So when you have the two, in the next progeny, you have M plus and M plus, then it's like 50% chance that the next group are going to be mutants and they're not.
yeah. So it is actually, you're right, statistically somewhat less likely that you would have two independent M's entering the same pedigree, particularly if M is relatively rare. If M is quite common, however, suppose M were something was a 20% frequency in the population, then it actually might be quite reasonable that this could happen. So what would you really want to do to test this? Sorry? Well, if you found any females here, maybe you'd be able to conclude that that it was autosomal recessive because females never show a sex-linked trait. Is that true? No, that's not true. Why not?
Because we had white-eyed flies when it was on the X chromosome because they had both.
You're right. So you just have to be homozygous for it on the X.
Right.
So having a single female who has it won't. I mean, she's not going to take that as evidence.
Yeah, but you can check to see when the female has children, you can check to see if all the males have the sex-linked trait. And,
Get an affected female and demonstrate that all of her offspring, all of her male offspring, show the trait.
and none of the females, because if she's going, only if you cross it with normal. Yeah, if you
Cross her with it. Wait. This is a human pedigree, guys. Woo! There are issues involved here, right? You can introduce her to a normal guy, but whether you can cross her to a normal guy is not actually allow. So you see, these are exactly the issues involved in making sense out of pedigrees like this. So what you have to do is you have to collect a lot of data and the kinds of characteristics that you look for in a pedigree, but they are statistical characteristics, and notwithstanding, so this could be color blindness or something, but notwithstanding, you know, the pictures in the textbook of color blindness and all that, you really do have to take a look at a number of properties. What are some properties? One you've already referred to, which is there's a predominance in males if it's X-linked. Why is there a predominance in males? Well, there's predominance in males because if I have an X over Y, and I've got a trait here, I've got a mutation carried on this X chromosome, males only have to get it on one, females have to get it on both, and therefore it's statistically more likely that males will get it. So for example, the frequency of color blindness amongst males is what? Yeah, it's 8, 10%, something like that. I think it's about 8% or so. And amongst females, well, if it's 8% to get 1, what's the chance you're going to get 2? It's 8% times 8% is, it's a little less than 1%, right? It's 0.64%. 0.08 squared, no, sorry, percent. Okay, in females. So we'll just go 8% squared. So in males, 8%, in females, less than 1%. So there is a predominance in males of these sex-linked traits. Other things, affected males do not transmit the trait to the kids. In particular, do not transmit it to their sons. Right? Because they are always sending the Y chromosome to their sons. Carrier females transmit to half of their sons, and affected females transmit to all of their sons. And the trait appears to skip generations, although I don't like this terminology. It skips generations because of that. These are the kinds of properties that you have.